Exercise 214 is trying to train you to see lone pairs on an oxygen. It says, draw all the lone pairs on each of the oxygen atoms in the following structures. Before doing this, review Table 2.2, which I've included here, and then come back to these problems. Try to identify all the lone pairs without having to count, and then count to see if you are correct. So there you have a shortcut here. The shortcut is, if an oxygen ever has a negative charge, then it's going to have one bond and 3 lone pairs. If there's no charge, it'll have 2 bonds and 2 lone pairs. And if it has a positive charge, it'll have 3 bonds and 1 lone pair. So you could memorize that, and you could go through these and fill in the lone pairs that way. If you ever forget that, though, all you have to remember is that each of these oxygens need to have 8 valence electrons. That's when they're stable. If you remember, oxygen is in group 6A. 6A, that means it has 1, 2, 3, 4, 5, 6 valence electrons. It has 2 electrons here that are unpaired and so not very stable. The oxygen becomes stable when somehow it pairs those electrons with something else, and that's usually with a bond. But notice that all of the electrons in oxygen are paired when there are 2, 4, 6, 8 electrons around the oxygen. Also, remember that a bond is 2 electrons. So if we were to look at this another way, you have 2, 4, 6, 8 electrons around that oxygen. So if we look at this first one, this is actually acetone, which some people use as nail polish remover. You can see that looking at that oxygen has 2, 4 electrons around it already. Each bond counts as 2 electrons. And to be stable, it needs 8. So we would have to add in 6 and 8. So 2 lone pairs. So we could see that. Now for B, if we look at this first oxygen here, you can see that has 2, 4 electrons around it. We add in the rest as lone pairs, 6, 8. And so that oxygen has 2 lone pairs. Remember that each of these counts as 1 lone pair. A pair is 2 of something. So this next oxygen here has 2 bonds, so that's 2, 4 electrons, and then add lone pairs until you get 8 electrons around the oxygen, so 6, 8. So that oxygen has 2 lone pairs. This next oxygen here has 2, 4 electrons around it, 2 bonds, and each bond has 2 electrons. So if there are 2 bonds, you have 4 electrons around the oxygen, and you just have to add 5, 6, 7, 8, 2 lone pairs around the oxygen to get 8 electrons around it, and to get all of its electrons paired. This next oxygen is a little tricky. If you have this structure, the OH here, it actually has a bond between it. There's a bond between the oxygen and the hydrogen that isn't being drawn. So it actually has 2, 4 electrons around it already, right? 2, 4 electrons around it. And so you would add 5, 6, 7, 8, 2 lone pairs on the oxygen to get a total of 8 valence electrons, so that all of its valence electrons are paired. For D, this first oxygen, it has 2, 4 electrons around it, so you add 6, 8, 2 lone pairs. This oxygen here has 2 electrons around it, so you add 4, 6, 8. That has 3 lone pairs around it. This oxygen has only 2 electrons drawn around it, so you'd fill in the rest up to 8 with lone pairs. So there's 4, 6, 8. That oxygen has 3 lone pairs. This oxygen here has 2, 4 electrons around it, 5, 6, 7, 8. We fill in the rest with lone pairs, so that oxygen would have 2 lone pairs. 1, 2. The oxygen in this molecule has 2, 4, 6 electrons around it. So it'd only have 7, 8, 1 lone pair. This oxygen here has 2, 4, 6 electrons around it, 7, 8, so you'd only add 1 lone pair. This is ozone. Protects us from getting skin cancer. It absorbs some nasty radiation from the sun in our atmosphere. So let's start first at the oxygen on the left. That has 2, 4 electrons around it that are drawn. The rest are lone pairs, so that's 5, 6, 7, 8. 2 lone pairs on that oxygen. The oxygen in the middle has 2, 4, 6 electrons drawn around it. You only need 7, 8, 1 more lone pair to get a total of 8. This oxygen on the right has 2 electrons drawn around it, and so you'd have 3, 4, 5, 6, 7, 8. So 3 lone pairs around that oxygen. For this last structure, first the oxygen on the top. That oxygen has 2, 4, 6 electrons around it. To get the 8 so that they're all paired, you'd have 7, 8, just 1 lone pair there. In this oxygen, there's actually an interesting thing happening here. You see a capital R there. If you look at the periodic table, no element has just a capital R. There are some that have like a capital R and an H or some other letter, but none has just a capital R. And in organic chemistry, capital R is sort of like an X is in math. An X in math could be any number. And R in organic chemistry is any carbon chain. So that could be any carbon chain. A carbon chain that's 2 carbons long, a carbon chain that's 500 carbons long. Doesn't matter here though, we're looking at the oxygen. So this oxygen, we want to know how many lone pairs are on it. Well, we need a total of 8 electrons around the oxygen. There are 2, 4 electrons currently around that oxygen. So you'd have 5, 6, 7, 8. 2 lone pairs around that oxygen there. And so these lone pairs are electrons that are going to be involved in reactions, and they're also electrons that may move around a molecule, as we'll see later in this chapter. So it's important to be able to see them on oxygens.